In today's video, we're going to be looking at a special type of sampling distribution, and that's going to be a sampling distribution of proportions. And before we start looking at some formulas and some characteristics, etc., let's just look at what we're doing. And we're going to have a particular population, and I'm going to say that the size of the population is capital N. That's how many people or things are in my population of size capital N. And there is a certain proportion that's true for this. Let's say we're looking at the proportion of people who have attached earlobes. So we know that you can have ears that have like a little dangle, and you can have, and that's not an attached earlobe. An attached earlobe would be where your ear does not have the little lobe that has a little, for no better terms, flaps around. So let's say I do not know what proportion of people in the United States have the attached earlobes, but let's say that just for the purpose of this, let's say attached earlobes, that the true proportion is 0.3. So if we're talking about a sample proportion distribution, what would happen is I would take simple random samples of a specific sample size, and I would collect some data, and I would find out how many successes I had. And let's say, for instance, I took a sample of size 200. And if I take 200 people and I count how many of those people of the 200 have detached earlobes, so 30% having the attached earlobes, I'll say it right, the attached earlobe, and if I divide that by 200, that would give me what we will call a p-hat. That would be a sample proportion. And then I would take another simple random sample of 200 people, and I would count how many of them have the attached earlobe, and I would divide that by 200, and that would again give me another p-hat, and that would be my second one. And we continue to do this over and over with a new group of 200 people, and we produce, all from the same sample size, a whole bunch of sample p-hats, each of these coming from 200 people, and counting how many people have attached earlobes, how many people have attached earlobes, etc. And we do this infinitely many times. And then we take these p-hats and we find the mean of all those p-hats, and if we have all of them, all the possible ones, this actually becomes a population mean of the p-hats, and then we could take these and find the standard deviation of all those values, and the standard deviation of all those values, if I don't have all of them, is an S of p-hats, but naturally we want to have infinitely many, all of them that are possible, each from a sample size of 200, and this would become a standard deviation, population standard deviation of all the p-hats. And so that's what we're trying to do, is figure out what would we anticipate as far as the center of all of these p-hats, and what would the standard deviation be of all of those p-hats. And it ends up, it has to do with the binomial distribution. So let's look at what we have here, and I believe I copied this down for you. So we know what a binomial distribution is. Binomial distribution has these four characteristics that we talked about in the last chapter, but we're looking at how many successes we have in a fixed number of trials, n trials. And we know how to find the mean number of successes if we have n trials. We take n times p. We also know how to find the standard deviation of the distribution. And if we kind of think of the distribution for a binomial setting is, again, dealing with how many successes we have, and the distribution we're going to talk about today is going to be the proportion of successes we have. So a binomial distribution is for counts. It counts how many successes. So n times p is our mean, count, and n times p times 1 minus p square rooted measures the variability of our counts for that sample size of n. Now we're going to change the situation, and we know if we want to change the count to a proportion, we would take how many and divide it by how many successes divided by the total number that we would have had in our sample. So in reality, we actually expect, go figure, the mean of all of the p hats, as I looked at in the other circumstance, to be p. And we can actually figure out the formula for standard deviation of p hats by taking the standard deviation for counts, which we already know from our previous study of binomial distributions. And remember, we change a count to a proportion by dividing by n. And if we take this standard deviation and divide it by n, this will be our standard deviation for the proportions that I was discussing earlier. Now I just did a little algebra. And in order to get this n underneath the radical, I would have to rewrite it as a square of n square rooted. And then notice that this n cancels out one of these n's, and I end up with this formula for my predictable pattern. So if I go back and I look at my little picture here again to relate what these formulas are going to mean, when I take all these samples of size 200 from this population of people, say in the United States, and again, this is a known parameter, at least I'm saying it's a known parameter, and when I sample, and I get these individual p hats, each how many successes out of 200, how many successes out of 200, and so on, I actually expect the mean of all of these p's, if I do this over and over and over again, taking all these p hats, I expect this mean proportion to be, go figure, p, which is 0.3. Now, I don't expect all of these proportions to be the same. I'm not going to get 30% every single time when I sample 200 people from a large population. This is what I expect the variability to be. I expect it to be the square root of p times 1 minus p over n, which means I expect it to be, for this scenario, for our little picture that we had here, I expect these p hats, these numbers, to vary like this. 0.3 times 0.7 divided by 200. And if I go back and figure out what that calculation is, that would be the measure of my standard deviation for this situation. And again, we're going to do more examples of this as we go on. So let's look at our notes. So when we're talking about sample proportions, there is a true population proportion. As in my case, it was that 30% for the attached earlobes. And a p hat is a sample proportion. That would be if I take a sample of size n and I count how many people have attached earlobes and then divide it by how many I had. That would be an example of a sample proportion, or of a p hat. Now, our sampling distribution is where I'm comparing lots and lots and lots of these p hats to each other. And I find that the mean of those p hats will actually be equal to the p value, or the distribution will center at the true proportion p, as long as I take these simple random samples. And the standard deviation, or how variable each of those p hats will be from each other, if I look at many of them, will have this measure. And so we kind of proved the formula, or showed the connection between a binomial distribution. So the mean and standard deviation for a binomial setting, if we simply divide and make these proportions, divide this by n, divide that by n, we actually come up with these formulas. Now, going back to this little picture I had before, and remember I described the total number of people that were available to look at their earlobes as capital N. And that sample was a little n. And I'm going to continue to use that type of notation with this little description here. Now, your book happens to call this characteristic for a sampling distribution rule of thumb 1. Don't call it rule of thumb 1 for me. You basically, I'm just marking it as this so you could go back and refer to your book. But you will want to know what this formula is, as far as, or what the rule is, but not based on rule of thumb 1. So first of all, this standard deviation formula that we have right here is the correct formula as long as your sample is no more than 10% of your population. In other words, if I take my sample size, multiply it by 10, I need my population to be larger than or equal to that, which means I need my sample size to be no more than 10% of my population. If my sample size, say, had been 200, but my population had been 500, then this sample would actually be 40% of the population. And this formula is not the appropriate formula to use for a standard deviation formula under those circumstances. So we first of all do need to look at, can we use this standard deviation formula to describe our sampling distribution? And as long as our population is size, the number in our population is greater than or equal to 10 times the sample size, again, meaning that our population is not being sampled by any more than 10%, then this is the appropriate standard deviation formula for our sampling distribution. Now we have another quote rule of thumb, which again, you're not going to refer to it as rule of thumb 2. You'll actually refer to what it means. But sometimes this sampling distribution, and remember what the sampling distribution is. I'm looking at p hat, p hat, p hat, p hat, infinitely many p hats, and I graph them. Sometimes, just as a binomial distribution has a characteristic that looks bell-shaped or approximately normally distributed sometime, that is also true for a p hat distribution. And in fact, we're going to use the same rule to determine whether a binomial distribution is approximately normal as we do for a sampling distribution of proportions. So we will use normal approximations when our n times p, which is the number of successes that we expect, and the n times 1 minus p, which is the number of failures that we expect to have in our sampling, is at least 10. So as long as both of these are at least 10, our distribution will be approximately normal. Now let's turn the page. So I have an example. And in the example, we have the Gallup poll asked a probability sample of 1,785 adults whether they attended church or synagogue during the past week. And this book comes directly out of an example or a question from your book. So it sounds like kind of an odd number of people to sample, but I just wrote down what your book said from their sampling. Now, suppose that in reality that 40% of the adult population did attend. Now, we actually don't know this. We're just saying suppose this is true. We would like to know the probability that a simple random sample of size 1,785 would come within plus or minus 3 percentage points of this true value. So let's look at and kind of break this question down and see what we're supposed to understand from this. Okay, so think you have a large group of people in the United States. This is in the millions. We are sampling a simple random sample of size 1,785 people. We're also supposing that the true proportion is 40% having the characteristic of attending a church or synagogue during the past week. So first question is explain why I can use the standard deviation formula for this setting. And I'll think about what this even means. What I'm trying to do is I'm going to sample and I'm going to get a specific number of successes out of 1,785, and that would be called a p-hat. Now I'm thinking about doing this over and over, collecting another sample of the same size and getting a p-hat, and doing it again and getting a p-hat. And I'm wondering, can I use the standard deviation formula on the previous page to describe how these p-hats will vary? I know I'm not going to get 40% every time. And I can. Why? Because my population, which I don't know the exact number, but I know that the population of people in the United States is going to be greater than or equal to 17,850 people. So I can appropriately use that standard deviation formula. In fact, what is that standard deviation formula? we take the p times 1 minus p divided by the sample size, square rooted. So I anticipate that these proportions are going to have a standard deviation of 0.0116 or about 1%, because remember all these proportions could be turned into percents as well. Just like this 0.4 could be called 40%. Now what would the mean of my p hats be? The mean proportion, or all these little p hats that I'd get, if I found these, added them up, and divided by how many I had, I anticipate that I'm going to end up with 0.4 or 40%. Now, will these p hats be approximately normal? Next question. So I have a test, the same as the test that was for our our binomial distributions in Chapter 8. We need to test what happens when I multiply n times p. I expect 714 successes, and I expect 1,071 failures. Since both of these are way greater than 10, my distribution of these p hats, if I graphed them, got a whole bunch of them and graphed them, my distribution will be approximately normal, and it will center here and have this standard deviation. So I said draw a picture of this distribution. So I centered it at this proportion, and I have roughly a 0.01 or a 1% standard deviation for my p hats. So since it's approximately normal, we can draw the bell-shaped curve. And now we can also use normal calculations to answer probability questions. So the question asked us at the beginning, we would like to know the probability, right here, we would like to know the probability that a simple random sample of size 1,785 would come within plus or minus 3 percentage points of this true value. So let's go back down to this picture. What does that mean? We want to know if we go up to about 43% or go down to about 37%, what percent of the time would our sample p hats be within that region? And this is our sampling distribution. I don't know about you, but it looks like it's going to happen most of the time. Well, let's calculate it. So here are my calculations. Now, note the notation. This is the probability situation I'm trying to find. I am having a p hat as the value I'm looking for. I'm not going to put this as an x, because an x would mean that I'm dealing with counts, and I'm dealing with proportions. Now, since we have an approximate normal distribution because of that n times p, n times 1 minus p, we can convert this to a z-value. I find out in both cases I'm about 2.6 standard deviations higher or lower than the mean, with those being plus or minus 3 percentage points, or being from 0.43 down to 0.37. And that's going to happen about 99% of the time. Now, I have one more example that we'll go through. Oh, good, the bell's ringing. And at this point, if you want to stop and work and then turn the video back on after, that would be fine. But I'm just going to keep going. The little ever-ready bunny, I'll just keep going. All right, suppose we have a random sample of 200 pregnant women, and we're trying to find and look at the statistic we have here, or this actually parameter for this setting, that 70% of people, of women, plan to go back to work within 2 months of having a baby. So we're going to assume that this is the true proportion for a population of pregnant women. And so think about my picture. Here are all these, capital N would be all the women who are pregnant, and we're going to take random samples of size 200, and we're assuming that 70% do plan to go back to work. This is going to be a very large number of people. And so we're going to sample, and we're going to get p hats and ask people, do you plan to go back to work? Take the number that are success, divide by 200, and produce p hats, and get many of them. And we're thinking, how will these p hats center, and what variability or standard deviation will they have? So what are the mean, standard deviation, and shape of the distribution of proportions of women who are going to go back to work within 2 months. First of all, the mean of all of these proportions should center at 0.7 or at 70%. Now, secondly, I have to question, can I use this standard deviation formula? Yes, I can. If I take 10 times my sample size, the population of pregnant women will be higher than that. Therefore, this formula is appropriate to use. Now, next, do I have an approximate normal distribution? Yes, I do, because n times p and n times 1 minus p are both going to be way bigger than 10. I expect to get 140 successes, and I expect to get 60 failures. Both those numbers are way larger than 10. Therefore, my distribution will be approximately normal. Now, I have some notation in here about the continuity correction. Don't worry about that. I'm not going to hold you responsible. So I have, using a normal approximation, sketch the probability distribution of p hats. Smack dab in the center is the proportion of 0.7, and then I know my standard deviation is about 0.03, and I drew out 2 standard deviations to the left and right. Now we're going to find the proportion of times that we would anticipate sampling a size 200 and having the proportion of women who say, yes, I plan to go back to work within 2 months, finding what percent of the time will we have that percentage or that proportion be between 67 and 73%. So here's our question. Sorry, you may not hear the announcements, but I'm hearing an announcement blaring in my ear. So we're trying to find the answer to this question. And notice that when I look at this graph, I can see it looks like it's going to be close to 68%. So it's a little bit less than 1 standard deviation away. But I take these values, convert them to z-values, and find the area between. Now, we could also do this with a binomial calculation. And with a binomial calculation, if I go through and change this to counts and find out what number of women would I expect if this was 67%, that comes out to be 134. And what number of women would be at 146, and that, at 0.73, that would be 146, or 0.73 times 200 gives me this. And so if I want to do this with a binomial calculation, I really am finding from 135 to 145. We could write that in a sigma notation. And remember, we have a combination. We have a probability of success. We have a probability of a failure. And if we let this go from 135 all the way up to 145, this would count and calculate it with a binomial setting. And naturally, I would use my binomial CDF in order to do that. And I would end up getting about 60%. Now, notice these percents are not dead on the same. And part of that is because of this idea that the normal distribution allows for you to have all the decimals that are between these values, whereas a count only lets you allow specific whole number values. So we do have a way that we talked about in the last unit as well of going through and doing a little correction that, again, I'm not going to hold you responsible for. Now, I did one more little calculation showing what would happen if I actually included the endpoints and had this be inclusive. And remember, for a normal distribution doesn't care whether you include them or don't include them. It's not going to vary its probability. But unfortunately, with the binomial setting, if I include them or don't include them, I get quite a bit of a different probability setting. But in any case, really the average of these two is very close to this value. So I will not hold you responsible for going through and finding, including, not including, and finding halfway between. basically, if you do something with a binomial setting, I'm going to be happy if you do either one of these. There are approximations to a situation that is not perfectly normal nor perfectly binomial. So any of them would suffice. You've got about a 65% chance. Okay, and that will be it for today's video.